So I'll be talking about a system to verify network behavior of known cryptographic clients. I'm Andrew Chi, and this is joint work with Robbie Cochran, Marie Nesfield, and it's been advised by Mike Reiter and Cynthia Sturton. Okay, so let me begin by actually describing the problem that we're trying to solve. So suppose we have a client-server application, and we'd like to defend the server against an untrusted client without necessarily knowing the server vulnerabilities and without knowing the exact avenue that a malicious client might take. So in order to do so, let me describe our threat model in some detail. So in general, untrusted clients can exhibit any behavior, but the particular class of misbehavior of interest for this talk is what we call invalid commands. And what I mean here, an invalid command is when a client exhibits behavior as seen by the server that is inconsistent with the sanctioned client software. So to better illustrate what this means, it's helpful to compare this to a much more limited attacker, and this is what we're showing below here. This constrained attacker has full control over the inputs to the legitimate client program, but cannot actually execute arbitrary code. So in the context of an online game, you'd think an attacker might control all the key presses and mouse movements, but all of the updates and commands that are actually sent to the server are produced by the unmodified client program. So that's the one in green down here. And as such, all of those are valid commands. In contrast, the attacker on top can send impossible commands to the server, such as shooting through walls, or it can craft malicious packets that actually attack the server directly. So going back to the definition, the invalid commands are exactly the difference between these two scenarios. And as we define it here, any behavior that is possible for the top attacker but not for the bottom attacker, that's the invalid command. And it can take, as we said before, the form of a maliciously crafted packet, or it could take the form of a set of well-formed packets, but in an impossible order. Okay, so now how does this distinction help us defend the server? Well, an equivalent way to say all of this is that if we have a mechanism for detecting invalid commands, then we constrain all would-be attackers to the bottom limited behavior, even though we're actually living in the top world. Okay, so now when would this be useful? So the notion of an invalid command attack can apply to online games, but it also applies equally well to lower layers of the protocol stack. So one part of the protocol stack that's really important, but also particularly tricky to get right, is the cryptographic protocols. Case in point is transport layer security, or TLS, which in our work we use it as our driving example. So quick reminder about what TLS is. The TLS protocol sits on top of TCP, provides protection to the application layers above it, such as web or email. It's made up of a handshake, which gives you authentication and key exchange. It's got a record layer that actually protects the traffic, and it's got a couple of other things like alerts and heartbeats. Now, TLS is a pretty good protocol and is widely deployed. Unfortunately, it's been in the news a lot, which is the opposite of what you want for a security protocol. So we looked at the vulnerabilities in the last couple of years for OpenSSL, which is one of the main implementations of TLS. And it turned out that over half of them involved invalid commands. The most infamous of these, of course, is one that everyone's heard of, Heartbleed. And so Heartbleed was an implementation bug in the OpenSSL heartbeat handler. It basically affected all OpenSSL applications for 2 years, which was like 500,000 web servers, so non-negligible proportion of the internet. So you might think that, given its severity, Heartbleed was really sophisticated, but actually it's so embarrassingly simple that XKCD made a comic explaining it. So normally, a TLS heartbeat is a keep alive. So the client asks the server, "Are you there?" Sends a random string, say the 3 letters HAT, and if the server is there, it echoes the string back. This figure shows a malicious client, which sends hat, but lies about the length and says it's 500. So the server then echoes back hat, and then 497 bytes of whatever else was next to it in memory, including other people's data, passwords, or the server's private keys. So, oops. Of course, this is a bug in the server where once you know about it, it's an easy fix. The question is, how can we defend the server if we don't know about it yet? So the key is that the attacker's message here is an invalid command. So how do we defend the server? We defend the server using what we call behavioral verification, and that is we permit the authorized client software's behavior only. So this eliminates entire classes of attack without knowing about them beforehand. So now, one naive way to do this is to simply have the server just rerun the client code, but that means the client has to send over all of its inputs to the server, so key presses, mouse movements, random number generator outputs. And that means that we've modified the protocol, we've taken up extra bandwidth, and we'd like to do this without changing the client at all, since the clients are already deployed. And we'd like to do this quickly enough to enable rapid detection of exploit attempts. OK, so let's get a little bit more formal and precise here. The behavioral verification problem can be described as follows. So we're given a client program P and network messages M that we see over the network. What we're not given are the client-side inputs, so the key presses, the random number generators. And the question that we'd like to answer is this. Could program P have produced the messages M? Now, unfortunately, the general case is undecidable. And if you want to be specific, it's recursively enumerable. But for specific instances, not only may it be possible, it might even be practical to the point that we can use it such that if the answer is yes, we can permit the client to continue up in the right. And if no, we'll disconnect the client or raise an alarm of some sort. And in fact, we are actually building on work by Cochran and Reiter, earlier work that solved this problem for some simple online games like a two-dimensional space shooter. OK, so how is this done? OK, symbolic execution is the core technique that we use. And in particular, we extend the symbolic execution engine named CLE. One of the first initial use cases for symbolic execution was actually software testing. So suppose we have this function here called test_me, and we'd like to generate test cases that will give us full branch coverage, say. So first we compile the C code into LLVM bitcode and run it in a special interpreter. Now what this special interpreter does is it runs the function in a way that's different from normal execution. So normally the inputs to test_me over here, x and y, those are actual numbers which we call concrete values. Instead, the interpreter runs the function but leaves x and y not as numbers but as symbols. And as the program executes, x and y are kind of carried through and combined as formulas. So take the example here. When CLE executes test_me, z doesn't get an actual number. It gets the formula 2y. And then as it hits branch statements, CLE may split off into and explore both branches. So take a look at the case where we take both true branches here, and at the end, so we take both true branches, at the end we'll print LOL to the screen. In order for this to occur, it must be true that z equals x, so this first condition, or really 2y equals x, because that's what's inside z, and that x is greater than y plus 10. So both of those have to be true. The conjunction of these predicates is what's called a path condition. And once you reach the end, a SAT solver can be invoked to reveal a satisfying assignment. Here, x equals 30 and y equals 15 will work. And that gives us actually a concrete test case that will drive the program to this point. OK, so that was the original context for symbolic execution. How do we use this to detect the invalid command attacks? OK, let's say instead of printing LOL, the program on both true, where you take both true branches, instead the program sends z across the network. Then the behavioral verification problem is this. Say we see 42 go across the network. So the question is, could this program have actually produced 42? And the way we answer this question is that we add the constraint z equals 42 to the path condition and ask the SAT solver if there's a satisfying assignment. Now, of course, z was assigned the formula 2y. So the constraint we actually add down here is 2y equals 42. And in the case of 42, yes, indeed. The program could have produced it, and you can check that x equals 42 and y equals 21 satisfies each of these constraints. So up here, 42 is equal to 2 times 21, and 42 is greater than 21 plus 10. So we're good. On the other hand, z equals 41 is impossible, since z is actually equal to 2y, which means it has to be even. So for this simple example, that's it for behavioral verification. Given any number we observe over the wire, we can solve for whether it is a possible output of the program. OK. Unfortunately, it's not quite that simple for cryptographic protocols like TLS, and this is where our work comes in. So there are a couple of challenges introduced by crypto protocols. First of all, symbolic execution nicely handles variables with unknown values, like x and y in our previous example, but their sizes have to be known. So we knew that x and y were 32-bit ints. So unfortunately, some crypto protocols intentionally hide the sizes of their client-side inputs. So for example, when you do an SSH login, the protocol hides the length of your password by adding padding to it, and then, of course, encrypting the entire packet. So this does grow the search space, which then requires us to use parallelism to handle the inputs of different sizes. The details of how we parallelize symbolic execution are in the paper, but for the purpose of this talk, I'm actually going to focus on a second challenge of cryptographic protocols. So here's the second challenge. This second challenge is actually one that no amount of parallelism can overcome. So some functions are too costly to evaluate on symbolic inputs, whether the cost is memory or CPU or both. And we call these prohibitive functions. So in many cases, this is actually by design. So the AES block cipher is a very complex formula of key and plaintext. And without knowing the key, it's designed to be very difficult to figure out what plaintext would have resulted in a particular ciphertext. And even with the key, the resulting expressions are very complex. If you carry them through symbolic execution, this could be expensive. So fortunately, since we're defending a server, and the verifier process can be thought of as running on the server, or at least at the same trust level, we can actually give the verifier the session key. So we've got that. It's also often the case that because cryptographic protocols are designed to scramble messages in a way that can be unscrambled, you will actually eventually receive enough information to infer the inputs to some of these prohibitive functions. So we can actually defer execution of these functions until we have that info. And so here's the multipass algorithm. And I'm going to actually illustrate it in a moment, but let me run through it real quick first. So first, a user specifies the prohibitive functions. They're usually the symmetric and asymmetric crypto primitives and the hash functions. Then we run symbolic execution in multiple passes. And anytime we encounter a prohibitive function that we don't know the inputs for, we skip it for now and assume its outputs are unconstrained. Once we finish a pass of execution, then we see if we've learned anything about those inputs. And then we go back and see if we can re-execute. And this can cascade until we learn all the information that we need. So this should make a lot more sense with an example. So this is an abstracted subset of the TLS client source code you can think of. And it's running an AES GCM as its cipher suite. So suppose we're trying to verify a message over the wire on the right here. Can you guys see this mouse? Well, I'll try to describe it. So we've got capital A, T, C, and IV. So we've got kind of a Diffie-Hellman, elliptic curve Diffie-Hellman output. We've got a tag, we've got a ciphertext, we've got an initialization vector. The circuit kind of represents the program that we think the client's running. And there are unobserved inputs to that program. So these are the symbolic inputs on the left. So A is the Diffie-Hellman private exponent. We've got plain text coming in, say on standard in. And we've got an initialization vector, which is from a random number generator. So we've got elliptic curve Diffie-Hellman, which is prohibitive, AES, which is prohibitive, and we've got this Galois hash that is as well. We do assume that we have access to that AES symmetric key, K, which is part of server state. So imagine if you're running an Apache server and you have it you have it log the session key for network analysis purposes. Okay. All right, so now I think I've defined everything here. So first pass of symbolic execution, we execute from left to right. Well, unfortunately, if you look at every one of these prohibitive functions, there is something we don't know about its input. So we don't know the input to ECDH here, we don't know the IV for AES, and we don't know ciphertext for ghash. So actually, the first pass, we can't execute any of them. However, once we get to the end of the first pass, we reach a network send point, and then we can now set the expressions equal to what we saw over the network, the thing that we're trying to verify. And once we see that, we've learned all of these things. So we've learned the initialization vector, we've learned the public value of Diffie-Hellman, we've learned the ciphertext, we've learned the tag. Okay, so now we've learned all those, we can start over from the beginning again and execute from left to right. This time, AES, both of its inputs are known, so we get its output S. and ghash, the Galois hash, the ciphertext is known. So we can actually execute that and check to make sure the output actually matches the tag. Okay, and then finally at the end, since plain text was an XOR, is an XOR of S and C, we actually also learned the plain text. Okay, now notice that we never learned little a. This actually makes sense up here, because this is the Diffie-Hellman private exponent. If we'd actually learned this, then that means we would have found the discrete log of big A, which is, if we had done that, I'd be giving a different talk. Instead, so this remains unexecuted, and this amounts to the assumption that given big A went across the wire, there exists some little a that could have produced it. Okay, so after all of this, if we have not reached a contradiction, then we can actually declare the message on the right to be valid behavior. That is, it could have been produced by the client program here. Okay, so that's a multi-pass algorithm. Question is, does it actually work on OpenSSL, which is 500,000 lines of code? Okay, well, it turns out it does. We set up an OpenSSL command line client and server, which is, think of that as TLS without the application. Without the application layer, you have to literally type it in yourself. We modified the client so that after it performs a handshake, it sends the Heartbleed exploit. And then we also set up a behavioral verifier that watches this interaction and then verifies each message as it sees it. The verifier accepts all of the messages in the handshake, because all those were fine. But when the Heartbleed exploit was sent, the verifier couldn't find a valid explanation for the Heartbleed packet and then rejected the message as an invalid command. And it did this without any Heartbleed-specific configuration. We also tested an invalid command attack that was more complicated than Heartbleed, and you can find that in the paper as well. Okay, so it works. How fast is it? We measure the performance in the following manner. So we've got the client-server application. The verifier doesn't interfere with the communication, but monitors it. And for each message, we've got a message arrival time, on the left here, and then a verification cost in purple. That's the compute time. There's also possibly some time when the verifier is blocked. So here it's because message 3 can't be verified until message 2 has been completed. So combining the block time and the compute time, that gives us the verification lag. And that's going to be our primary measure of performance. Okay. So we applied this performance measurement to a realistic workload. We actually took our performance test set was 21 TLS sessions captured from 3 minutes of Gmail activity. We ran the Gmail application data over the OpenSSL, and we actually also did BoringSSL command line clients. And we ran a single core verifier on the resulting traffic. Overall, the average cost of verification per TLS record was 49 milliseconds. On the right, we've got a box plot of the verification lag over the 3-minute session. So the way to read this is that there's a bin for every 30 seconds of traffic, and for each bin, we're going to show the median down here, the upper and lower quartiles, the min and max and outliers, and the diamond shows the mean. So the main takeaway here is that the median lag is about 0.85 seconds, with a max of about 15 seconds at the initial burst of traffic. But fairly quickly, the verifier lag goes down to roughly keep pace with message traffic. So in summary, we can keep up with something like Gmail. In comparison to Heartbleed, which was in our servers for about 2 years, during which time our IDSs weren't even monitoring heartbeats, probably because we didn't think they were interesting. This is pretty good. Okay. We evaluated the system in a couple of other ways, which are described more fully in the paper. So we measured our parallelization performance by adding padding to TLS. So basically, we took the feature from TLS 1.3, or in draft right now, and put it in. We also made sure that we could detect a more complicated invalid command attack, where, unlike Heartbleed, every packet was legal, but the sequence is impossible. And finally, the nice thing about BoringSSL is that it's Google's streamlined version of OpenSSL, which is used throughout their infrastructure and in Chrome. So separately, we checked that, in fact, the BoringSSL command line client could be used as a reference to verify traffic from an unmodified Google Chrome browser. So we verified that our test harness faithfully represents the TLS layer of Chrome. Okay. And so in summary, we've demonstrated that we can accomplish behavioral verification for crypto clients. The MULTIPASS method handles the cryptographic functions, and parallelization helps with some of the expanded state spaces. So this enables us to detect previously unknown client misbehavior and, for example, detect a Heartbleed exploit with no Heartbleed-specific configuration. And we can do this fast enough to roughly keep pace with a Gmail TLS session. So that's that. And can I take any questions? Oh, how'd that get in there? This is this is our winning shot from last night from North Carolina.
So we do have time for questions, or we take off early for coffee break. But we do have a question. Please.
Hi, Keith Winstein from Stanford. I think this is really amazing work. I'm impressed you're able to keep up almost in real time. But what do you think this will do if people use this to interoperability? I mean, we like to be weirdos here in the research community. We like to write crazy clients that are legal by the spec, but maybe not what Google or a service provider will expect. What happens if the servers start enforcing that the clients behave, sort of how their preconceptions are?
Right. This is a great question. We are, of course, in this entire presentation, we're assuming that we know exactly what software the client is running. And so for certain protocols, that's actually OK. So for SSH, for example, the identification string is the first thing that gets sent. So you know exactly what software, what version. Certainly, we would want to gear this more towards constrained. Think like enterprise environments, where you know that everybody has to be running a certain version of software. I wouldn't apply this essentially on an experimental network, or maybe like completely on the open internet, where we want to allow interoperability with completely new clients, right? So this is something where you do have to be in a situation where you have an expectation of what's going to be running on the other side. Yeah. So that's a very, very astute observation. Yeah.
Shankar from AT&T Labs. So I had a couple of questions. I was curious how this can work against evolving client behavior, where the commands sort of evolve over a period of time, right? So how does that work? The second part of the question is, what happens if you have a combination of commands that are really, or the sequence of commands, or the combination of them not being the right ones that you expect?
Mm-hmm. So can you clarify that first question again? So you've got an evolving behavior over time.
Right. So you have a certain set of behaviors that you expect from the client, right? Okay. In terms of detecting these. So what happens if those behaviors evolve over time? Like, how fast can this be adapted?
Oh, I see. So for example, we go from Firefox 35 to Firefox 36.
Right.
Okay. Right. So it's certainly true that you do need the source code. It turns out once you've instrumented source code one version to do this verification, going to the next version isn't too bad. You do have to be a little bit careful about how you're going to handle multiple versions at the same time. And so you might, for example, run parallel verifiers, and if any of them accept, then it's good. Luckily, if the clients are significantly different, that means that you're going to detect really early on that it's really just one of them, so you're not wasting a lot of computation time. So that's the evolving client. And the second question, sorry, remind me again.
The combination of commands, right? Like.
Yeah. So right. So I showed Heartbleed, which was like the packet's just wrong. Because we're verifying the client logic, there was actually another vulnerability that we looked at where it was an authentication bypass where all of the packets were legal, but together in sequence, it wasn't possible for the client code to actually emit them, and the malicious client actually used this fact to try to get past the authentication on the server. So our verifier will essentially verify each message in sequence and keep the program state. And if the next message is impossible given the previous program state, it'll reject. Did that answer your question?
Yeah, thank you.
Okay. Yeah. Sorry. Yeah.
Hi, this is Alex Horn from Fujitsu Labs. I have a question regarding the size of the formulae that are being generated to check in CLI and the number of different paths you have to explore in order, for example, to find the Heartbleed bug.
Right. So the question, how big are the expressions? So it turns out that certainly with TLS, we're just sending large payloads of encrypted data, and so depending on, it's essentially proportional to how big your packet is. Luckily, they're not super complicated. For example, in AES-JCM, you've got essentially the output of the block cipher gets XORed to the plain text, and then that becomes the ciphertext. So you get long rows of expressions that look like that, these XOR expressions. And then in terms of the branching, for TLS, it's not too bad. There's certainly a lot of variation at the very beginning when sort of the cipher suite negotiation's happening, the handshake is happening. Once you actually get down into the record layer, where you're just essentially transferring bulk data, there's really only a few things that can happen. Either I'm going to send some more data, I'm going to receive some data, or one of the alert conditions. And so the number of branches per round, well, round meaning per message that we get, is probably only in the in like a few dozen for each stage in a normal circumstance. Now, if you go down a weird path, like once you get an alert or something and like a renegotiation happens, then you could explode again. But does that give you a sense for how big it is?
Sense. Just a quick follow-up. Did you use crypto-mini-set or the standard set solver in CLI in order to handle these XORs?
In our implementation, we are using crypto-mini-set, but I think it's pretty close if you just use the standard STP that it comes sort of shipped with CLI.
Okay, thanks very much.
Yep.
All right, let's
All right.
thank Andrew again.
Thanks.